continuing with chapter 27. Now we're going to explain how a quasar actually is a supermassive black hole. We're going to start by describing all the characteristics that are common to quasars, and I shouldn't really say all because there's not a whole lot of characteristics that are for both of them, or for quasars. First, hugely powerful. They emit more power in terms of radiated light. Remember, light is electromagnetic, radio, gamma, X-ray, all of it. They emit more power than all the stars in our galaxy together. And they are tiny, tiny. Solar system size or smaller. Some of them shoot out pairs of straight jets at close to the speed of light. We just looked at M87 and we're going to look at it again. The jets themselves are extremely powerful sources in both radio and gamma ray. Not so much in visible light. There is some. So now we're going to look at the center of the the center of M87. So, whirling disk of gas discovered at the center of M87. Take spectra from one side and the other side. One side is blue shifted, which, remember, Doppler, blue shifted means moving toward us. The other side is red shifted, which means that it is receding, it's moving away. This is clear evidence that, the disk is rotating. So we can measure the amount of blue shift and red shift and figure out that it is rotating at 550 kilometers per second. That comes out to 1.2 million miles an hour. So very massive black hole at the center of M87. Remember, once we know how fast it is rotating, we can use Kepler to figure out and Newton to figure out the mass. So, different galaxy, NGC 7052. This is an elliptical galaxy in Vulpecula. It's about 200 million light years from Earth. So, gas in the inner part whirls at a speed of about 155 kilometers per second. So that's 341,000 miles an hour. So with those and Kepler, we can estimate that the black hole in the center of NGC 7052 has a mass of 300 million suns. So this is not a stellar black hole. This is a supermassive black hole. And so how do we even record them? How do we see them? How does any of this work? So think about the Apollo spacecraft, and as it is dropping back, or any spacecraft, as it's dropping through the atmosphere, it compresses and heats up the air in front of it, pushing down the air, slows down the spacecraft, and it turns that kinetic energy into heat. So heat is visible because it, emits energy. So the really very fast moving gas around that quasar heats up in a similar way and emits heat. So in order to give off the amount of energy that we're talking about, it has to be very hot. In order to be that hot, it has to be very fast. Well, we just demonstrated that they're moving very fast. So, what happens to that energy from the jets? The Fermi spacecraft has recorded giant bubbles of gamma ray emissions, both above and below the center of the Milky Way galaxy. And this is thought to be evidence that our supermassive black hole was a quasar a few million years ago, or, more. So what causes the jets? Well, if we look at supermassive black hole, and it will develop an accretion disk of matter around it. The matter is spiraling into the black hole. Black holes are small, and immense gravity, but they don't just suck things in whole. Things have to spiral in, and so you end up with this mass of dust and cloud and gas and star particles that are spiraling in. If we have a thin accretion disk, then that jet, the energy that is accelerated out of the black hole, is going to be spread wide and not very particularly noticeable. However, if we have a really thick, fat accretion disk, it's going to only allow that energy to shoot out perpendicular to the direction of rotation of the mass. So what happens is that the mass is moving around the black hole, and then some tiny part of the energy, instead of falling into the singularity, gets a little bit of tweak on its direction of motion and shoots out the top of or bottom of that accretion disk. And so here we have an image of NGC 4261. The white is visible light, and the jets are shown in radio. And then a Hubble Space Telescope image showing the ring of gas and dust around that supermassive black hole. And so we can see that the jets really are perpendicular to the gas and dust ring, and that ring, you can sort of see that there is structure to the ring. The ring is kind of thick and fat, and so the jets shoot out. So I'm going to go ahead and try and finish this chapter up. So we're going to talk about, quasars over time and how they influence, each other's growth. So if we look at the fact that quasars, we have to look extremely far away in the universe to see quasars. Remember, when we're using telescopes and looking very far away, we're looking back through time. So quasars are something that formed very early in the universe, and the rate of formation of quasars pretty well matches the rate of formation of stars. So most of the quasars that we find were formed when the universe was, 20% as old as it is now. So very shortly after the Big Bang. And then we start trying to build a correlation between the mass of the central bulge of the galaxy and the mass of the black hole. And what we notice from observations is that there's a fairly linear line. As the mass of the central bulge of a galaxy gets bigger, the mass of the black hole gets bigger, and because there's this nice straight line, this suggests that there is a causal relationship somewhere. We just have to figure out where it is. And so when we look at real galaxies, the black hole turns out to be approximately 1/200th the mass of the stars in the galaxy. And so the horizontal and vertical lines show us the uncertainty of the measurements. We have to remember, in science, everything has, uncertainty. Uncertainty means error. What are the potential errors? So this black hole may be as, the central bulge may be as large as this or as small as that. Oh, and the black hole itself may be as large as this or as small as that. Anyway, but once again, we see this very linear relationship, and so we're building on the idea that, there seems to be a causal relationship. Either black holes form the central bulge of galaxies, hold it all together, or the central bulge of galaxies creates black holes. So we have to figure out which one it is. When we're thinking about black holes, one of the things to remember is, that we're looking at an artist image of 3 different times in the life of a star as it orbits around a black hole and, gets eaten. So we start with, nice round star, the way it should be. And as it moves in toward the black hole, it gets stretched. And then there is a point where the star shatters. The gases are all still very hot, so they're glowing as they spiral into this accretion disk, and so the accretion disk is really hot and glowing, but the star has been just obliterated. So we still need to really solidify this idea that supermassive black holes are what holds galaxies together, but we're almost there. And so with that, we are finished with chapter 27.